Hi everyone, I'm Jiacheng. I'm going to present the work Performance Interfaces for Hardware Accelerators today. This is a joint work done at the EPFL with Rishabh, Sahand, Mahyar, and my advisors Thomas Bourgeat and George Candea. Hardware accelerators are becoming integral in boosting system performance in various domains. For example, there are accelerators for speeding up machine learning, RPC message serialization and deserialization, network packet processing, bioinformatics, and many other domains. Now imagine using one of those accelerators for your workload. The first question you ask is whether it's input and output. Fortunately, hardware vendors provide you that. It's called a semantic interface. Semantic interfaces are documentation that tell you how to use the accelerator. The second, also the more important question you ask, is what and how much it accelerates. Unfortunately, you won't get an accurate answer because vendors only provide you numbers for benchmarks that may not be related to your workloads. Now, if you decide to blindly offload tasks to this accelerator, you might end up slowing down your workloads because accelerators can be optimized only for certain workloads and are not suited for yours. For example, the product accelerator for RPC message serialization can be slower than a normal Xeon CPU when the message is mainly long strings. To really get acceleration by using accelerators, engineers need performance interfaces that tell them how the accelerator performs under different workloads. Performance interface is similar to a semantic interface, but describes only the performance instead of the functionality. The idea of performance interface has been explored in the software domain, mainly with the works PIX and CFAR. Today, I'm going to show you a completely different methodology applied to the hardware domain. In this talk, I'll try to convince you the following three statements. First, accelerators must have performance interfaces. Second, accelerators should ship with a precise performance IR. And lastly, it is possible to build tools that then transform this IR into performance interfaces. Next, I'll show you what is a performance interface and how to use it. Then I'll talk about the performance interface, performance IR to represent the performance of the hardware and use it to derive the performance interface. And lastly, there's an Easter egg that I'll show at the very end, so stay tuned. Let's look at one example to understand what a performance interface is. On the right, I'll show you a performance interface for the product. Product is an accelerator for RPC message serialization and deserialization. The performance interface is a program that accepts the same input as the accelerator. In this case, it's a series of messages. The performance interface then returns how long the accelerator takes to process that input. Oh, by the way, the internal logic of product is quite complicated with massive parallelism. However, we can still understand its performance by just looking at this interface. For example, reading the interface, we know that the cost of serializing those messages is the sum of serializing each message. We also know that the cost of serializing messages of different types are quite different, and it depends on how many bytes are in a message instance. And very interestingly, we also know that there's a fixed cost to pay no matter how small your message is. Now, in just 1 minute, we understood so much about the product's performance, and most of you have never used the product and didn't do any benchmark. A good performance interface can be easily understood by human, and it is also executable. However, unlike a semantic interface, performance interface may not be as precise as the hardware, but slight loss of accuracy will not affect its usability. So I showed you what is a performance interface. Then let's talk about how to derive them. We cannot use the existing state-of-the-art because they are designed for software, and hardware is inherently parallel and asynchronous, which is fundamentally different from the software. We also don't want to directly extract the performance interface from the hardware source code or the RTL, because RTL is the wrong abstraction for this task. Now, if you look at this readable sequential human Python performance interface, and this parallel execution mode of hardware, there's actually a huge gap. Now, to bridge this gap, we propose performance IR. We first distill performance IR from the RTL, then transform this IR into an interface. This performance IR represents a performance equivalent circuit that finishes processing at the same clock cycle as the hardware given the same input. However, it does not produce the functionally meaningful results because it's not functionally equivalent. The ideal performance IR should satisfy the following requirements. First, it is an abstraction of the hardware that retains only performance-relevant information. Second, it is expressive enough to represent all sorts of parallelism and data dependencies in the hardware. And lastly, it should be formal, such that analyzable by automated tools. We came up with such a performance IR called latency patronate, or LPN, to represent the performance of the hardware. LPN is a parallel model close to hardware with natural constructs to represent the parallelism. LPN is based on patronates with several extensions, and the patronates have a long history of being used to model parallel and asynchronous systems. LPN also allows arbitrary functions to represent performance or data dependencies of those parallel hardware modules. Finally, LPN is abstract, expressive, and formal. Now let's look at the simplest LPN to understand its elements and how it works. This LPN, despite the simplicity, models the performance of a matrix multiplication hardware module. This hardware module implements a systolic array and takes in two matrices of size n by n and outputs the results after n cycles. This LPN has two places that models the hardware buffer that holds input data or output data. This LPN also has a transition that models the performance aspect of the hardware module. The associated delay function computes how long the hardware module takes to process the input that we put into the input buffer. In this case, the delay function computes how long the matrix multiplication takes given specific matrices. Finally, there are edges that connect the place and transitions. Now we can run this LPN to get the performance of the hardware. To do that, we first feed the input matrices as to the hardware to the LPN. The input matrices are then converted into a token that holds abstract features of the input. Here the token contains a property n stands for matrix dimension, and let's say dimensions for 100. Now this transition t is activated by this new token, which means it will consume the token after some delay as returned by the delay function, which is 400 cycles. So the transition waits for the clock to tick 400 cycles, then consume the input token and produce a new token with empty content, denoting that computation is done. Now, it is obvious that this LPN uses much less code than the original systolic array implementation to just represent the performance of the hardware. In fact, this is true for all 5 different real accelerators we constructed LPNs for, where we use only 10% of the code compared to the RTL to represent the performance. We can make this LPN more complicated by adding LPN modules for another hardware accelerator that loads the input matrices to a buffer, which then get consumed by the compute unit. This new LPN works the same way as before, but right now, the two transitions operate in parallel unless there are data dependencies, just like the hardware. Now, this gives you a feel of how an LPN works. The LPN abstraction we described in the paper is much more powerful than what we described here. So please take a look at the paper for more details if you're interested. With all the constructs provided by the LPN, we can turn a complex hardware design into LPN easily. The example shown on the left is a real ML accelerator VTA. It has fetch module, load module, compute module, and a store module. To turn this hardware into LPN, what we do is we build LPNs for the modules one by one and compose them together. The final LPN is quite similar to this architecture view of hardware, but with more details. Furthermore, the LPN can actually run and return the performance of the hardware, unlike a static architecture diagram, which is not actionable at all. Because LPN matches closely to the hardware, it is easy for hardware engineers to produce an LPN by hand. Based on our experiment, a hardware engineer could construct an LPN in a few hours after understanding the hardware for a non-trivial design mentioned used in programmable switches, which has around 10,000 lines of valid code. LPN is also very expressive, and we were able to capture different performance-related details for all 5 accelerators which constructed LPNs for. The LPNs are also accurate with 1.7% average error across all 5 accelerators we evaluated. The inaccurate part is a result of simplification from RTL, but not due to the limitations of the LPN itself. Now remember, there's a huge gap, a big wall, between this parallel execution mode of hardware and the readable sequential performance interface. With LPN, we found a way to bypass this wall. Furthermore, we fully closed the gap with a tool we built called LPN2PI that transformed the LPN into the performance interface. LPN2PI takes the LPN and an input space of interest, then produces a program, which we call the performance interface, that computes execution cycles of the hardware for every input in that space. LPN2PI aggregates delay functions in the individual transitions into the program. And in this process, they also take into account the parallelism and data dependencies of all the transitions. LPN2PI uses the input features or aggregation of those features as free variables in the program for the interface to be human-readable. So LPN2PI produced performance interfaces are human-readable, and the price we pay for readability is that the performance interface is less accurate than the LPN. But the good news is that the average error is only 20%. Now we have looked at what performance interfaces are. We also saw the performance IR, LPN, that makes deriving the interface possible. Now to this Easter egg I've promised, which is with LPN we can actually do much more beyond performance interfaces, because LPN is a very efficient IR for performance. We extended the transformation toolchain with LPN2Sim that produces a fast performance simulator. The simulator produced is 1 to 3 orders of magnitude faster than a state-of-the-art RTO simulator. Workloads that actually depend on simulators, which normally takes hours, now take seconds to run. So what used to be a batch mode workflow is turned into an interactive mode for the software engineers. We also developed LPN2SMT that produces SMT constraints from the LPN, which can then be used to formally verify performance properties with the solver. We use the LPN2SMT to prove upper bounds that a hardware JPEG decoder takes to do its job. And this is crucial for real-time systems that needs performance guarantees of hardware accelerators. We also used LPN2SMT to find a performance bug for the hardware JPEG decoder itself and found an underprovisioned buffer, which improved the performance by 37% after just one line fix. We can even use LPN2SMT to prove the maximum prediction error introduced by a performance interface compared to the LPN. Please refer to the paper for more details and explanation. To conclude, this talk made the case that accelerators lack performance clarity, and to fix that, they must have performance interfaces. They should ship with a precise performance IR, and we propose LPN for that. Tools should then automatically transform this IR into performance interfaces and many other useful representations. This work is a part of a larger project on performance interfaces for both software and hardware. And on the project website, you can find the LPNs and a fully open source toolchain. Thanks for your attention. I'm ready to take questions now.